May 16010 Fall 2022 Exam 3 Walkthrough. Let's begin. 1. Which of the following limits is equal to infinity? So, we need to check every single one of these, unfortunately. Let's start with A. The limit as x approaches infinity of negative x to the fourth minus a over x squared plus 3. So with all these limit problems, it's really, really important to look at the powers of the numerator and denominator. You can pretty much disregard the rest of the terms as long as you only look at the ones with the highest power. So for example, the highest power in this a is this x to the negative, or x to the fourth, and then this x squared in the denominator. So over time, this will start to look like negative x to the fourth over x squared, and then even later in time, it starts to look like negative x squared. Because this is going to infinity, we can say that this will go to negative infinity, which means that A is not the answer because we are looking for the limit that equals infinity. Moving on to B, highest power is x cubed. The highest power in the denominator is x to the fourth. So again, over time, our function will start looking like negative x cubed over 3x to the fourth, which then even further on in time will look like negative 1 over 3x, which means that this goes to 0. If the highest power in the numerator right here is higher than the highest power of the denominator, so in this case 3 is smaller than 4, the limit will approach 0. So this is also not the answer. C, as the limit as x approaches negative infinity of 5 plus x squared over x minus 1. In this one, the highest power is x squared, and the highest power in the denominator is x. Over time, it will look like x squared over x, which means that will end up being x. But because this limit is evaluating as x approaches negative infinity, this limit actually is negative infinity. So C is also not the answer. D, the limit as x approaches infinity of 3x minus 2 over x cubed plus 1. The power in the numerator is x to the 1, and the power in the denominator is x to the third. The numerator has a power less than the denominator, so this will approach 0 again because our function will look like 3x over x cubed after a long time, but after an even longer time, it'll look like 3 over x squared, and 3 over a very, 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 very large number will be 0. So this is also not the answer. E, the limit as x approaches infinity of negative x squared plus x minus 4 over x plus 9. This power in the numerator is the highest with x to the squared, and the highest power in the denominator is x to the first. So that means over time, our limit will start to look like this, negative x squared over x. Then, and even further along in time, it will look like negative x. And as negative x goes to infinity, this goes to negative infinity. So E is not our answer. And that leaves us with F. That means F must be the answer. But we will go ahead and evaluate this too. The limit as x approaches negative infinity of negative 2x cubed over x squared plus 2. The numerator's highest power is x cubed, and the denominator's highest power is x squared. So over time, this will look like x negative 2x cubed over x squared. And even further along in time, it's going to look like negative 2x. And because this is evaluated as x approaches negative infinity times a negative number will be positive, so this goes to positive infinity, which is what we wanted. So again, the limit that equals negative infinity is F for number 1. Number 2. For rectangles that have a fixed perimeter of 36, what is the largest possible area? So this is an optimization problem. If we remember the perimeter of a rectangle, if we draw a rectangle out, we have two sides that are x and two sides that are y. So the perimeter equals 2x plus 2y, and that means that 2x plus 2y equals 36. Now we're looking for the largest possible area. The area of a rectangle is x times y, or length times width. So to find the largest area, we need to find where the derivative equals 0. Unfortunately, we still have a we have two different variables in here, so we can't really take the derivative yet. But because we have this other equation up here, we can solve for either x or y and plug it back into this area equation so we can actually derive. So I'm going to go ahead and solve for x. So if we were to rewrite this, we would say 36 minus 2y equals 2x, which means x equals 36 minus 2y over 2, or 18 minus y. We plug this x back into this area equation, and we get area equals 18 minus y times y. I'm going to go ahead and distribute to make this easier. So it'll be 18y minus y squared equals area. Again, to find the largest possible area, this is an optimization problem. All optimization problems have some sort of derivative equaling to 0. So we're going to take the derivative of this area and set this equal to 0. So a prime equals 18 minus 2y is the derivative of y squared is 2y. Set this equal to 0. Solve for y. 2y equals 18. That means y equals 9. Plug this 9 back into this x equation to find x. X equals 18 minus 9, which means x equals 9. And we're asked for the largest possible area. So if we re-plug it back into our area equation, we get a equals 9 times 9, which equals 81, giving us an answer of F. Number 3, the integral of 1 over 2 square root of x plus e to the x dx. So the great thing about integrals, if two things are added together, we can do them separately. So I'm going to do this in two parts. Essentially, this is equal to the integral of 1 over 2 root x dx plus integral of e to the x dx. So I'm going to start with the harder part, which is that left part. So when I do these, I really like to write these with, if the x is in the denominator, I like to write with a negative root. So we say 1/2 x to the negative 1/2 is what we're finding the integral of. So to find the integral, we have a leading coefficient, so we're just going to write that, times 1 over the new power. The new power will be negative 1/2 plus 1, so that's positive 1/2. So 1 over 1/2 times x to the negative 1/2 plus 1, which is 1/2. If we simplify this, that simplifies to 1 over 2 times 2x to the 1/2, which simplifies to the square root of x, as these two will cancel out, and x to the 1/2 is square root of x. The integral of e to the x, the second part, is super, super easy. The integral of e to the x is quite literally just e to the x. So if we add these two together, we would get the integral of 1 over 2 root x plus e to the x dx equals square root of x plus e to the x plus our integration constant. Don't forget it. That constant basically stands for something we may have taken the derivative of, and we don't know what that value is. For example, a constant like 1, if we take the derivative of 1, we won't know what it is when we integrate. So, looking at our answer choices, this matches with the answer of E. If you're unsure about the answer you get on an exam, you can actually derive this to get back to this original equation. I'll do this right now. So x to the 1/2, the derivative of x to the 1/2 is 1/2 root x, and then the derivative of e to the x is e to the x. So we're all good. So again, our answer for 3 is E. Number 4, consider the graph of the derivative of the function f of x. Which of the following is true about the function f of x? So if you look at this statement again, it says the derivative of the function of f of x, which means that this graph is actually f prime of x. This is important because that completely changes our interpretation. So the first thing I would like to do is look for anywhere this derivative crosses 0. So it crosses 0 right here, which means that at x equals 3, there is a min or max. Now, how do we know if this is a min or max? Well, side is positive, then this side is negative. So if it is increasing, so this first part right here, if it is increasing and then decreases, that means we have a max, because that means our graph would look something like this, where it's increasing and then decreasing. So at x equals 3, we have a max. It's also good to point out at this point that there are actually no other relative extrema other than this point, because there is only one point where the derivative crosses the x-axis. So if we look at our answers, we can go ahead and get rid of anything that has a relative minimum, or both a relative minimum and a relative maximum, because again, we only have one extrema. So if we look at our answers, E has no relative extrema, so that's wrong. F has both, so that's also wrong. D is wrong because we have a max. C is wrong because there is relative extrema. And then B is wrong because there's not both. So our answer is A, but I wanted to point out where the two inflection points in this answer are. So the derivative or inflection points occur when the second derivative x equals 0. So that means that there's a peak or a dip in the first derivative. So we can actually see our two inflection points here, where the slope of the derivative or the second derivative equals 0. So our two inflection points are at x equals 0 and x equals 2. Again, our answer is A. Number 5. Use left Riemann sum to approximate the area under f of x equals 2x squared plus 1 from x equals 0 to x equals 6 with 3 rectangles. So with these Riemann sum questions, I really like to draw a picture. I think it helps a lot. So if I draw a quick picture, it's going to be really rough and kind of ugly, but it does the job, so I can't complain. Okay, and 2, 4, 6. So you might ask why I marked my x-axis the way I did. We have the interval from 0 to 6 with 3 rectangles, and 6 divided by 3 is 2, so that's why I have marked my axes in intervals of 2. So if I draw my left Riemann sum, that means the left of the rectangle is touching the curve. I might have drawn this curve a little too shallow, but should be good for now. So this graph or drawing shows that we need to find what y equals at x equals 0, x equals 2, and x equals 4, because for those respective rectangles, that's where they touch the curve at those specific points. So I'm going to put in f of 0 equals 2 times 0 squared plus 1, or 1. And then we're going to find it at f of 2. F of 2 equals 2 times 2 squared plus 1, which equals 9. And then this last point right here for 4 is f of 4, so equals 2 times 4 squared plus 1 equals 33. Now, we're going to go find the area of each of these rectangles, starting with, let's call this rectangle 1. So for rectangle 1, the area is 2, that's this width right here, times the height, which is this right here, or the 1, so that means that the first rectangle's area is 2. For rectangle 2, same thing. The width is from 2 to 4, or 2, times the height. The height is 9, so the area of rectangle 2 is 18. And then for rectangle 3, again, 4 to 6, that rectangle has a width of 2 times the height, where the left touches the curve, is at 33. So 2 times 33 is 66. And then if we add this all together using your calculator, 2 plus 18 is 20, plus 66 is 86, meaning that our left Riemann sum is 86. So with left Riemann sums, you want to use a height of the left part of the rectangle. But I think it's a little bit hard to see unless you draw a picture, so I always recommend drawing a picture. Number 6, find the slant asymptote of f of x equals 2x squared minus 5x plus 9 over x plus 1. Whenever we're given a question that asks about a slant asymptote, the first thing you gotta think is polynomial long division. So we want to set up our long division. So I'm going to write the numerator under the bracket. So 2x squared minus 5x plus 9. And then what we're dividing by, x plus 1 on the left. Now, polynomial long division is a little weird. So we try to basically match this term to the largest term. So by multiplying by something. So for this first one, we want to say x plus 1. What times x will equal 2x squared? 2x. So we line this up. So 2x squared plus 2x. Subtract that. And that gives us minus 5x minus 2x, which is 7x. And then we move the 9 down plus 9. So what times x equals negative 7x? That is negative 7. So we need to multiply that by negative 7. So we have negative 7x minus 7. That whole thing subtracted to cancel these two right here out. And then we are left with 9 minus 7, which is 15. But that's unimportant because the slant asymptote is this top part right here we found. So that gives us y equals 2x minus 7. If we look at our options, that gives us f. Number 7. The rate of growth of dp of a population of bacteria is given by dp over dt equals 4t, where p is the population size and t is the time in days 0 to 10. The initial size of the population is 400. What is the population after 5 days? So something super important to note is this is the change, right? So a really common mistake might be to plug in 5 days because you might assume that the population changes by 5 every single time. But unfortunately, that's not really the case. When you're given a question like this is basically a separable differential equation. Not that that's super important right now, but what they want you to do is to integrate to find what the actual p population function is. So we're going to do that. So dp over dt equals 4t, so p equals the integral of 4t dt. We're going to integrate this. 4 over the new power, t is to the 1, so t to the 1 plus 1 is t squared, so the new power is 2, so divided by 2 times t squared plus c. Do not forget that integration constant because that is super, super important because this function could literally be anywhere if you didn't consider this constant. Now, if we simplify this a little bit, we get 1/2 t squared plus c equals p. Now you might be wondering, what's c? Well, we are given an initial condition right here. So if we plug in 0 for t, because that is the initial size, we should be able to find c. So p is 400, because that's the original size, equals 1/2 times 0 squared plus c. That means that c equals 400. So that means p, or the population function, equals 1/2 t squared plus 400. Now we can plug in the 5 days here, so we get p equals 1/2 5 squared plus 400, which equals, oh, not 1/2, oops, oh no, I said 1/2 almost the whole time. I meant 2, so let me fix that real fast. 4 divided by 2 is not 1/2, it is 2. So if I write this out, it still doesn't affect our constant because 2 times 0 is 0. So if I fix this, we get p equals 2 times 5 squared plus 400. So 2 times 25 plus 400 equals 50 plus 400, or 450. So that means our population after 5 days is D, 450. Other than my minor mistake, again, the process is just to take the integral so that we can find the original population model or equation. Number 8. Consider the function f of x equals x squared plus 2x plus 1 over 2x minus 8. Consider the following statements. 1. F of x does not have a horizontal asymptote. Number 2. F of x has a vertical asymptote. Number 3. F of x has a slant asymptote. And number 4. The x-intercept of f of x is -1, 0. So the first thing to note, we're going to start with the first statement, does not have a horizontal asymptote. Well, if the numerator's power is greater than the denominator's, then there is no horizontal asymptote. So as we can see, the highest power in the numerator is 2, and the highest power in the denominator is 1, and because 2 is greater than 1, this does not have a horizontal asymptote, which means that this statement is true. Number 2, f of x has a vertical asymptote. When we're looking for vertical asymptotes, we are looking at this denominator. Anywhere this denominator becomes 0 or making the whole thing non-existent, there is a vertical asymptote. So there's a vertical asymptote at x equals 4 because at 4 this denominator would equal 0, which means indeed there is a vertical asymptote. Number 3, f of x has a slant asymptote. So if there's not a horizontal one, there is usually a slant one. This one, if the numerator is greater than the denominator, then there is a slant, which means that when we prove the first one, we inadvertently also prove the third statement true. So f of x has a slant asymptote. Number 4, the x-intercept of f of x is -1, 0. So if we're trying to find the x-intercept, we just need to plug in 0 for f of x or y. So 0 equals x squared plus 2x plus 1 over 2x minus 8. We can multiply the 2x minus 8 to the other side, so we get 0 equals x squared plus 2x plus 1. If we factor, we get x plus 1 times x plus 1. So that means that there's a x-intercept at -1, so this is also true. That means that our answer is F. All of the above is true. Number 9, solve the initial value problem. Y double prime equals 5 cosine x, y prime of 0 equals 1, and y of 0 equals 2. So they're wanting us to find what y equals as given by very clearly all of these answers. So we are given the second derivative. So how do we find what y equals? Well, we just have to integrate twice. So let's go ahead and do that. Y prime equals the integral of y double prime, which equals the integral of 5 cosine x dx. So if we take the integral, we get 5 integral of cosine is positive sine x plus c. Don't forget that integration constant, it's super, super important. So you might be asking, what is c? Well, we're giving an initial value that helps us solve for this c. So if we plug in 1 for y prime and 0 for x, we should be able to find c. So 1 equals 5 sine of 0 plus c. Sine of 0 is 0, so that means c equals 1. So that means that y prime equals 5 sine x. It's a really ugly 5 actually. 5 sine x plus 1. Now, let's integrate again to find y. So y equals the integral of y prime, which equals the integral of 5 sine x plus 1 dx. So the integral of 5 sine x, be careful with your signs. The integral of sine is negative cosine, so that'd be -5 cosine x. And then the integral of 1 it's a constant, so you just make it x, so plus x plus c equals y. Again, you're given in the initial value in the problem statement, so we can solve for this other c. So if we can plug in 2 for y and 0 for x, we should be able to solve for that c. So 2 equals -5 cosine of 0 plus c. 2 equals -5 times cosine of 0 is 1 plus c. That means that c equals 2 minus a -5, so 7. So if we rewrite this, kind of running out of space here, we get that y equals -5 cosine x plus 7. If we look at our answers, that gives us f as an answer. Oh boy, there's been a lot of f's actually in this entire problem. Again, be careful with your signs with your sinusoidal functions. Number 10, find the right Riemann sum that approximates the area underneath the curve of y equals natural log of 2x plus 2 on the interval of 0 to 4 with 8 rectangles. Give the answer in sigma notation. So again, with the Riemann sums, I like to draw a picture. I think it helps with visualization. It doesn't need to be perfect. It just kind of needs to look what it's supposed to look like. So natural log functions kind of look like this. It says on the interval of 0 to 4 with 8 rectangles. So that whole interval is 4. 4 divided by 8 rectangles. That means the width of every rectangle is 1/2. So if I draw my rectangles with a right Riemann sum, they look like this. 3, 4, 5, 6, 7, 8, with every other rectangle being a full number. Now it asks for it in sigma notation. So the first thing to note is that all of the answers that don't have a 1/2 in front of it, aka the width, are wrong. So that includes D, E, B, and A. Again, because we have established that each of our rectangles are 1/2. So the summation needs to be that width times that height plus the next rectangle's width times that one height. So we are down to 2 answers because only C and F have a 1/2 to account for that width. Now, the only difference between the two is where it starts. This is important because for right Riemann sums, we want I to start at 1 because the height starts at we're using the point at which the rectangle, the right end of the rectangle touches the curve. So if we were to write this, we would get I equals 1 to 8 because there are 8 rectangles. So 1, 2, 3, 4, 5, 6, 7, 8 of 1/2. So this is the width of the rectangle times I plus 2. So we keep the 2, but the reason that this 2x becomes I is because 2 times 1/2 is just 1. So that 1 becomes the I. So every rectangle, instead of being 1/2 and then the next value is 1/2 and 1/2, in sigma notation, we can only go up by full numbers when we're summing. So to account for that, we basically just half that x, that 2x, to make sure that our rectangles are every half when we do the notation. So again, that means that our answer is F because we are starting from the right side. So the first, the point at which the right of the rectangle touches the curve is at the right, which means we start at 1 and not 0. So again, our answer for number 10 is F. The summation from I equals 1 to 8 of 1/2 ln I plus 2. Number 11. Find the x-coordinate of the point on the graph of y. This is supposed to say equals. Had a little bit of transcription error. Y equals 4x minus 9. That is closest to the point 0, -5. So when we're doing a distance to a point, one thing to note is that we are actually using a derivation of Pythagorean's theorem. So given that this is x and this is y, we want this distance to be minimized, or d. So we can say that d squared equals x squared plus y squared, or that d equals the square root of x squared plus y squared. Now, we want this distance to be minimized, so like in every optimization problem we ever do, we need to take the derivative of this d. However, we do have a y here, and this is not exactly yet in the correct form, and I'll explain why. So we're going to write this d equals the square root of x squared minus the x coordinate of the point 0, or not x squared, okay, x minus 0 squared plus y minus the y coordinate, which is -5, so -5, that whole thing squared. The reason we write it like this is because we need the distance to the point, and if we were to just have x squared plus y squared, that would be our distance from the origin. So we need to account for the shift to the actual point you want, so we need to include this -0, which won't be relevant afterwards, and this -5 to account for the shift in points because we are not trying to find the distance from the origin. Now, we still have a problem with this y because we can't really derive y, but we are given what y equals in this equation, so we can actually just replace this y with 4x minus 9. So we can say that d equals the square root of x minus 0 squared plus 4x minus 9 minus -5, so that's +5, that whole thing squared. If we simplify a little bit, we get d equals the square root of x squared plus 4x minus 4 squared. Simplify again, that gives us x squared plus 4x times 4x is 16x squared. 4x minus 4, or 4x times -4 is -16x minus another 16x plus 16. So again, this last part right here is just this distributed. Now, if you simplify again, we get 17x squared minus 32x plus 16. But because this function is always increasing regardless of the root, we can just pretend this root doesn't exist. And that will make our derivative much, much easier. So I'm going to actually make this smaller and get it a little bit out of the way so I have a little bit more space. We now say that d equals 17x squared minus 32x plus 16. Again, we're trying to find what the closest distance is, so we're trying to minimize, which means that we need to find the derivative of this distance equation and set it equal to 0. So let's go ahead and do that. D prime equals 17x squared. The derivative is 17 times 2, which is 34x, minus derivative of 32x is 32. Derivative of a constant is 0. Set this equal to 0. We get that 34x equals 32. And then x equals 32 over 34, which if you simplify by dividing by 2, you get 16 over 17. If you look at our options, that gives us an answer of B. And last question. Bob is building an open top wooden box for his cat who likes to play with boxes. Bob is using wood on all 4 sides in the bottom and is covering the wood on the bottom with carpet. Bob would like the bottom to have a square base. The cost of the wood is $3 per square foot, and the cost of the carpet is $1 per square foot. The cat requires 18 feet cubed to have a satisfactory play in the box. What is the minimum total cost of the box? That was a mouthful. Anyway, so this is another optimization problem, because these are always so much fun. But anyway, optimization problems always come with 2 equations. One so that you can just the overall equation, and then one to help you solve that said overall equation. So if we look at what we're doing, Bob wants a box. So here's our box. Bob wants a bottom to be a square base. So this means that this has length x and this also has length x, but the height can be anything. So this height is y. So if the cat requires 18 feet to have a satisfactory play, we can say that the volume equals x times x times y, which equals x squared y. And this, x squared times y, must equal 18 because that's what we want in volume. Now, we need to figure out the cost of this box, or equation for the cost of the box. So, wood is $3 per foot squared, and carpet is $1 per foot squared. If we write our cost equation, we need to know how many panels of each thing we need. So we need 1 bottom panel and 4 side panels. We only need 1 bottom panel because this top is open, so there's only 1 bottom or 1 square. So if you write out the cost equation, we can say that the cost equals, let's start with the bottom panel because it's the most complicated. It has both the wood, so a cost of 3, plus the carpet, so plus $1 for the carpet, times the area, which is x squared. So we can check this again. This 3 plus 1 is the cost, so that would be dollars per foot squared times the area, leaving you with only dollars. So that's a check for units. Anyway, moving on to the next part. There are 4 side panels, each with area x times y, as you can see in our diagram, and they all have a cost of $3 per foot squared. So again, we can check the units on this one. With these word problems, I really like to check the units. 4xy, so that's 4 panels times the area. That will have a unit of feet squared, times 3, which has a unit of $3 per foot squared. Foot squared times dollar per foot squared is dollar, and dollar is the unit we want for cost, so that's good. So this is an optimization problem because it says what is the minimum total cost of this box. So we need to take the derivative of the cost equation. However, we can't take the derivative with this y, but we have this equation from earlier, which we can use to solve for y, so we can only derive with one variable. So from this equation, we can say that y equals 18x squared. If we plug this y in here, we get that the cost equals 3 plus 1 is 4, so 4x squared plus 4 times x times 18 over x squared times 3. Now, this should be a lot easier to take the derivative, but I first want to simplify a little bit more with the constants to make this easier to see. So we can say c equals 4x squared plus 4 times 18 times 3 is 216 if you plug that into your calculator. And then x over x squared is just 1 over x, so 216 over x. So our cost equation equals 4x squared plus 216 over x. Now we take the derivative so we can find the minimum cost. So c prime equals 8x plus 216, take that back, 8x minus 216 over x squared equals 0. So again, the derivative of 216 over x, that is just the derivative of 216x to the negative 1. If we do that, we see that it's negative 216 over x squared. So we have the derivative of our cost equation. Let's solve for x. So we get that 8x equals 216 over x squared, which means that 8x cubed equals 216, which means that x cubed equals 27, and then that means that x equals 3. So if I move everything over a little bit, because I'm running out of space again, we get that x equals 3. So now we can solve for y with that equation. Y equals 18 over 3 squared, which means that y equals 18 over 9, which means that y equals 2. So this problem is not asking for x and y, it's asking for the minimum total cost, so we need to plug it back into our original cost equation. So C equals 4 times x squared, which is 3 squared, plus 4 times 3 times 2 times 3. So I'm pulling from this line right here. If we simplify that, we get, using our calculator, we get 36 plus 72, or that the cost equals $108. So that was a big mouthful, but essentially what we wanted to do is we wanted to create a system of equations where one is the volume of the box, because that is one constraint, and the other one is the cost. We basically drew a picture to figure out the different panels and how much each panel would cost, and then add it all together. We took the derivative of said cost and set it equal to 0 to find the minimum cost, because wherever the derivative equals 0 is where there could be a min or a max, in this case a minimum. Then we solved for x, then we solved for y, and we plugged those back into the cost equation to get the overall cost, which was again D 108.